All right, I think we're good to actually say a few things, get going here. We'll definitely do some math today, but I feel like there's a few class logistics we should go over before we get to the fun math part. We'll do the boring class part. So I'm James, in case that wasn't immediately clear to all of you. I'm one of the math specialists at the AATC. Welcome to class. We'll go over the Canvas stuff, which hopefully isn't too terrible. And also feel free to ask questions whenever you have them, raise your hand or whatever. I feel like there's something else I want to say before you do that, but no, I guess, yeah. So we'll go over the Canvas stuff. There's really, as far as this class goes, from my perspective, as far as passing this class, if you're enrolled in this class, there's kind of two things you need to know. Thing one, you need to fill out the attendance form when you come to class. And thing two, you need to do the weekly reflections. And that's kind of it. The other thing I guess you should know is that if you're not actually enrolled in the class, you didn't use a CRN to sign up for it, that's great. You don't have to do either of those things. So if you're not enrolled, you don't need to worry about your grading class. So you're going to see, all of you are going to see a grading canvas. If you're not enrolled in the class, you can ignore that. It doesn't matter at all. If you are enrolled, meaning you registered via CRN using Schedule Builder, then you definitely do need to worry about that. So that's the difference. And I'll probably, that's gonna love. I'm gonna trip over this and die someday. I will probably write something, some announcement in Canvas at some point, just to re-clarify that for everybody, because usually through the quarter, people go, "Hey James, I'm worried about my grade." So I'll remind you that I'll remind you who that's important for and who it's not, but we'll talk about that later. So let's look at the Canvas here. So here's my Canvas dashboard. Lovely. Let's make this a little bit, I feel like it's kind of huge. Let's make that a tiny bit smaller. There. So Canvas, wonderful. Let me show you a couple things that you may or may not be aware of. Something I always think is useful is that if you click right here on any of your classes, you can change the nickname of the class. I usually like to write the time and place of it. So you can see I've written there, it meets, whoops, you could have seen, let me go back to the dashboard, that I have written that this class meets Tuesday, Thursday, 9 a.m. And I also wrote the CRM because I often need to access that piece of information. I've also written the classroom sometimes to remind myself of where it is, but you can write anything you want there, just in case you didn't already know that. It's kind of useful, I think. As you can see also for like the actual, like I'm in the, where to go here? Somewhere in here is the actual 17B Dedel class. I wrote his name on there, so I remember which class that is. Yeah. Speaking of which, show of hands, who is in Dedel 17B class? All right, who's in Temer Galiaba's class? All right, so definitely large proportion Dedel. So for those of you in Temer Galiaba's class, we're probably going to skew more towards what Dedel is doing. Not that that won't be good for you, because what he's doing is probably going to be harder, to be perfectly frank. Not that her class is easy by any means, but Dedel is always the hardest. I'm not gonna lie. He is the harder teacher. That's just true. He's going to expect more of you, but also the other classes are still going to be a lot of homework. So both classes going to be a lot of work either way. So don't feel like you're getting the short end or the long end of the stick because you're in one class versus the other. Both are going to have a lot of work. I feel like Temer Galia might have more homework in her class, but Dedel definitely has more content maybe. So like there are extra things he will do that maybe the other teacher will not do. Also, fun fact, I had Dedel as a teacher when I was a student here over 20 years ago. Yeah, for my linear algebra class. He's a good teacher. Like he's still here for a reason. He was a good teacher then. I think he's still a good teacher now. All right, anyway, to the Canvas. The one place in Canvas you really will end up wanting to use is the modules. So we'll look there real quick for a second. This will be the home page after the first week, but the first week it's on the syllabus, so you can all see the syllabus. When the modules, eventually you'll see the course evaluation near the end of the quarter. That's not important right now. You will see these useful links, like the link to the attendance form, the link to the Zoom, my office hours, Grant's website, which is always useful, my website, which is not useful. And oh yeah, we'll talk about this later. There's a really nice graphical tool for looking at the Riemann sum. I think it's a really lovely thing. We'll talk about it in a minute. And then down here, you'll be able to find the class recordings and the written notes that I'll post up after the class. And that's really, and then maybe other like practice exams and stuff. Anything useful for the actual mathing of math will be found here. All the other kind of not useful but important class stuff we'll find over in the syllabus. So we'll go through this as quickly as we can, and then we'll get back to the math. All right, so, oh, and also, yes, is there a copy of the handout on Canvas? There is not, because I just made it, but I will post it after class. There's something else I wanted to say. Oh yeah, for those of you on Zoom, feel free to write things in the chat. You might have noticed it took me a good, what, I don't know, 2 minutes to see what was written in the chat. If I'm not seeing the thing written in the chat, you are welcome to unmute yourself and say words. You might scare me to death. That's all right. I will still answer your questions. But if you've written something in Zoom, feel free to actually ask it with words as well. I just might forget. But yeah, please do ask questions. I'm just looking, usually I'm not looking over there, but I'm looking over there right now because of the way this is set up. So I guess I could double my screen, but it always feels like it's a mistake. So you can find the Zoom link here. The best way to get a hold of me is by email, to be perfectly honest. You could call me, and I will pick up my phone if I'm in my office, but nobody calls people on the phone anymore, right? I mean, that's not a thing people do. You can also just come by my office. You can also find me in office hours, which are these times and places. Monday, Wednesday, Friday, 10 to 11:45 downstairs. Friday's only 10 to 11 though, or 10 to 10:50. Monday, Wednesday, Friday in the afternoon in CADS, which is the Center for African Diaspora Student Success in the South Silo, room 270 on the second floor. Anyone's welcome there. You're welcome to come find me. There's usually, at least typically, that's a place where less students come find me. So if you want more attention, that's a good place to come see me because I'm usually less occupied with people. Tuesdays and Thursdays for right after class-ish, over in C class, which is the Center for Chicano, I always forget the X, Chicanx Latinx Academic Student Success. That's over in the MU on the second floor, like right kind of by the flagpole. You go up those little stairs there above the coffee house. And then finally, Tuesdays and Thursdays from 1 to 3 in math drop-in down in the library. That will start, the math drop-in specifically starts next week. So I won't have those office hours today or Thursday, but starting next week, I will have those office hours as well. All the other office hours are this week. So right after class, I'll have office hours over in C class from 10:45 to 11:45. I feel like I'm talking a mile a minute. I will try to slow down a little bit. Sometimes I talk too fast, which is not my usual personality, but definitely when I teach, like I just tend to get going. So the grading for this class, so this only matters for those of you that register for the class of the CRN. For those of you that just signed up to be added to Canvas, which I think is the majority of you, because I think I added like 30 of you to Canvas the other day, this doesn't apply. For those of you that did actually register for the course using Schedule Builder, you want to pass the class. Passing the class is easy. You just have to do 2 things. No, I guess 3 things technically. Thing 1, which is really 2 things, is come to class and fill out the attendance form. Speaking of filling out the attendance form, here's how you can do that. You can, if I can find the thing. Not those QR codes. I use my own because I know, sorry, I'm doing it differently. I use my own QR code because I like to collect the data that I want to collect and then sort through it that way. Also because if you use that one, it all goes to a larger thing where everyone says, then sifting through that to update the attendance on Canvas is more challenging. So I would like everybody to be able to see this. There we go. Oh, yes, that's terrible, James. Come on, get that a little bit more. So hopefully you can scan that. And I'll also put up a couple around the room so you can scan those as well. It does say class attendance, yeah. Go here, going up here, it may be here. And what I would, or you could also just go to the Canvas for class and find the link there, which might be easier than trying to scan a thing. And what I really recommend for everybody, and you should all do this whether or not you're actually registered for the class, because I would like everybody to fill out the attendance form regardless of your actual status. There's a reason for that, which I'll explain in a minute. But I'm saying something and now I lost my train of thought. Oh yeah, you should bookmark this page. Bookmark it so you don't have to scan this thing every time. Does everybody know how to bookmark a page in their like web browser? Like you hold on a little bookmark thing and then like pops up and asks you to bookmark it. And then for those of you on the Zoom, here's the attendance form you fill out. Let me show you all. So here's the form. It looks like this. You enter your UC Davis email, not your other email. Your student ID number, all 9 digits. Your name, here's how I would write my name, James Parmenter. First name first, last name last. As it appears in Canvas, and I do ask you to do this specifically because I'm going to then look in Canvas later and take this data that comes in a Google Sheet and update your Canvas attendance record so that you can see, especially for those of you that are actually registered for the class, what your attendance looks like. Because your grade is basically based on your attendance. So do this the way that makes it easy for me to update your attendance later. Sometimes it takes a minute for me to update the attendance. So if you when you fill this out, it doesn't automatically like update your Canvas attendance, just so you know. And then the class you're attending, that would be Co-17B. How you attended, live in person, live virtually, or you watch the recording later, which we'll talk about. And then the class that you're attending for. So let's say you're not here right now. I know you all are. And you watch this on Friday, April, what, 5th? Yeah. The date you would fill out would still be the date the class actually occurred. So if you watch this later, you're still going to write the date as 4/2, and please write the entire 4-digit year so that it shows up in the right order. And then you would click submit, assuming you done. I didn't put a date, but my ID or anything, but that's what you would do. It's pretty straightforward, I think. Are there questions about it? So please do this every time you attend in person, you attend on Zoom, or if you watch the recording later to make up attendance for a class you missed. The one thing I ask is that if you're making up attendance later, not ask, the one thing I require, it's like there's not a lot of like sticking points for me, but there's one. And the one sticking point is I want you to make up attendance within 2 weeks of the actual occurrence of class. So if you miss today's class and you're making it up later, you have to make it up by what? 2 + 14 is April 16th. Make sense? Okay. And then not only do you need to make it up within that time, you also have to fill out the form within 2 weeks. I'm not going to take attendance, at least not by like writing it down myself. I'm going to take attendance by you filling out this form. So you do need to fill out the form. It's the one thing you really need. Well, it's one of the 2 things you really need to do. I've had people not pass the class because they just didn't fill out the form. Please fill it out. It's not hard to do. Okay. The other thing that that I require of you to do is the weekly reflections. They're not hard. They're pretty straightforward. Let's go look at them for a second. You can find them in the assignments. There's one that is due April 5th or due April 3rd. It'll close April 5th. So you do need to do that kind of soon. I know it's a little bit soon, but let's look at the first 2 here real quick. Here's what they look like. Tell me your name, what you prefer to be called. I will try to learn your names. There's kind of a lot of you, so I might be less good at learning your names than I often am. If you come to office hours and tell me your name a few times, I will definitely learn your name. Your hometown, where you would like to be from, that's a different question for me. Something you did over spring break, interesting or not. And what math class you took last quarter and what your grade was. I imagine most of you took 17 last quarter, but some of you might have not taken 17 last quarter. So yeah. And then also you can always send me a joke, a meme, a pun, something. I like the jokes. And then after the first one, after that, they kind of become pretty similar. I'm usually going to ask you, what did you do in your actual 17B class this week? And then how you think you're doing in your class? Is there anything you want to see me cover in class the following week? This is also why these are typically due on Friday, I think, or maybe Thursday, but they won't actually close until the following week. I would like you to do them kind of as soon as you can so that for the upcoming week, I have an idea of what you would like to see in class. Really, this is mostly so I know what you want to see in class. You might want to see about the anti-power rule or the integral, the limit definition, something like that. And then usually there's something kind of like something about your personal self, like what's your favorite color or something maybe a little bit more interesting than that, but just kind of a throwaway question for lack of a better word. But I'm not asking you any math stuff here. I'm not asking you to do a thing really other than just answer a few pretty straightforward questions, I feel like. So please do these. Again, if you're not actually enrolled in the class, you don't have to do them. but I would like you to do them if you have the time to do them. If you are enrolled in the class, you do actually need to do these so that you pass the class. Because we have to have you do something to pass the class. We can't just give you a free unit. I would totally give you a free unit if I was allowed to, but there are rules about making students do things for units. So these are the things you have to do to get the unit. Hopefully that's relatively not terrible. Any questions so far? Back over here. Hopefully you all were able to fill out the attendance form. Go back to the syllabus because there's probably a few other things I need to say. Let's see, that's where you can find me. Grading. So 70% of your grade is based on attendance. The other 30% is based on the reflections. A passing grade is 75% or higher. So obviously you have to do at least a couple of the reflections to pass the class if you're trying to pass the class. Because there's 10 reflections and they're worth 30%. Each of them is worth 3%. You got to do at least 2 of those to make up the 5% you won't get from the attendance that you need to get. Okay. So do them all. They're easy. Here's the attendance form again. If you're absent for any reason, you're welcome to make up the absence by watching the video and then filling out the attendance form within 2 weeks of your absence. Not passing isn't the end of the world, but anyone who's enrolled in this class can pass if you do the things. About this class, let's see, what have I written here? If something outside of this class is impacting your success, please come talk to me. I'm happy to help. Students have definitely come to me before with things their teacher was doing that I tried to help them with and sometimes was successful. If I do anything terrible, you can come talk to me. You can come talk to my supervisor. That's not going to happen. But maybe I'll say something accidentally that I'm not aware is maybe idiotic. That's not generally my vibe, but who knows? You can always talk to my boss. Jen is great. She will definitely listen to you wonderfully. Or her boss, Sarah, your teacher last quarter, also great. Tell them, but really, like, I don't anticipate that being an issue, but it's good to say the thing anyway, just in case. Who knows? What else? Our class is here at this time. You all know that because you're here at this time. I'm going to show you stuff. I'm going to ask you to do math. Come prepared to write things down is what I would say. Accommodations. If you have accommodations, any accommodations, I've already received some. Most of the accommodations seem to be about making recordings or needing more time or stuff like that. There's no tests in this class, so you won't need extra time. I'm happy to accommodate whatever needs accommodating. If you need to record something, that's fine. I do record everything and post it. I also post the notes, so I don't think that's necessary. But again, if you need to, totally fine with me. But yeah, everyone knows how Zoom works at this point. I feel like I can probably not keep adding the Zoom instructions here in the syllabus. Some notes about the class. It's worth a workload unit if you signed up for that. You could, although no one ever has, use the discussion tab to ask questions in Canvas. Actually, that's true. One person did one time. It was great. People responded. The thing that I like about the discussion tab in Canvas is someone can ask a question and one of you can answer it. Or I can answer it, and I can also write in nice math writing there, which I can't in other places. So if you have a question that you want to ask me, you could ask it using the discussion tab in Canvas. It's right here. And oh yeah, there's something there that I actually don't want to post that, but that's all right. I will delete that later. But yeah, you can ask the question right here, and then I could respond. It'd be lovely. You should try it. Maybe, maybe not. Probably not, but that's all right. You don't have to. What else here? Yeah, you're gonna spend at least 10 to 20 hours in this class for sure, because Dadell is gonna ask a lot of you, as is the other professor whose name I feel like I'm never saying right. Tamergaliava, is that how she say it? Close enough? Maybe, I don't know. I think some people call it Dr. T. Okay. Where can you get more math help? From me in office hours, from the other math specialists, Sarah, Grant, Claire, forget Jen. There's also math drop-in starting when? Next week. I don't know if it starts on Sunday or on Monday. But Mondays it's from, I think it says right there actually. Yeah, Monday through Thursday, 12 to 5, and Sunday 3 to 7. That's what you can find student tutors or myself on Tuesdays and Thursdays from 1 to 3. I think Grant's down there some of the time as well. I don't think Jen or Sarah are, but we can find, and also you can find us in other places. Sure, let's just do that. If you go to the tutoring.ucdavis.edu/math for the AATC website, if you scroll down a bit, a bit, you can find the specialist office hours. So for myself, Grant, and Sarah, this is when and where you can find us across campus. Yeah. All right. I think that's it as far as the syllabus goes. All right. So let's take a breather. Any questions? Well, if you have questions later, you're always welcome to ask them, or you can ask them after class privately, or whatever you like. So I imagine, oh wow, I really am spilling water here. That's not wonderful. Paper towels up here? No. Usually there's some paper towels around here. So everybody had class yesterday, I imagine. And I know in the Dallas class, you all talked about like what I call the anti-power rule, and also some like Riemann sum stuff. How about in Dr. T's class? Similar-ish? No, what did y'all talk about in her class? Power function? Okay. Sure. Sure. That seems totally reasonable as well. Okay. Gosh, sorry. I'm trying to like wipe up the water I spilled here so I can write on page it over here. Okay, I think that's all right. Sure. So this handout is fine. I did write it. It's okay. Also, for those of you that maybe didn't catch this earlier, you might not be able to see what I'm putting here. Let's do that. Cool. Yeah, let's get this a little bit more. Let's maybe move that cursor out of the way, James. Sorry, I know. So a few things about me just in general. Sometimes I'm not sure what's going on over there. So if you can't see something that I'm writing, let me know. Sometimes I get too high or too low accidentally. I don't do that on purpose. It's just this classroom is not equipped with a little screen here that shows what you're writing. And I like having other stuff up here, not the duplicate of what's over there. So if I'm off, just tell me. Just say, hey, James, we can't see what you're writing. Or also, in that same vein, if I've written something that is hard to discern because my handwriting isn't always excellent, just ask. I'm happy to clarify if that's a 5 or an 8 or a 4 or whatever number I'm trying to write or whatever word I'm trying to write. But the thing I want to clarify here is that really this part I just want to kind of scratch out, but specifically if you want to make this sentence correct, you should cross out the anti part here, because it is correct that the derivative of 3x minus 8 is equal to 3, not the antiderivative. But really, I was talking about antiderivatives, so I want to kind of cross this entire line out. I meant to write something else there, but ran out of time. So really, that can just go away. And also, this is kind of, let me fix this a little bit here so it's not in the way there so much. Cool. I feel like there's something else. Oh, does the F without a line symbol for the, yeah. So let's talk about some notation and some symbols here. So we'll come back to this handout in a moment. Let me get this cursor, it's killing me. There we go. Okay, cool. So yeah, I want to be down here. So I say the word so a lot. Try not to, but we all have our little linguistic kind of places we fall back to. We are in Co-17B. Again, in case you missed it, this is Co-17B, not Co-16B. Co-16B is with Claire. They also meet at this time, but via Zoom. And today is April 2nd. Ooh, yeah. Oh, it's kind of a palindrome. I like that. Next class, we'll talk about some fun calendar stuff, which is not important at all, but I like to talk about it. So, antiderivatives. When I think about antiderivatives, I think about the fact that we are kind of undoing what a derivative does, or that antiderivatives and derivatives undo each other. That's my kind of main place. It's kind of similar, not exactly the same, but similar to how inverse functions undo what the other function does. So let's actually look at that for 1 second. Let's talk about inverse functions for just a brief moment. I'll give you a really easy example. Here are two inverse functions. F of x equal to 3x plus 2. It takes your input x, multiplies it by 3, and then adds 2. And then the inverse function, f inverse of x, does the opposite things in the opposite order. Instead of multiplying by 3 and then adding 2, first we're going to subtract 2 and then divide by 3. Yes, there's a more kind of systematic way of finding an inverse function, but when the functions are linear like this, it can be kind of fast to just find the inverse by talking it out. And what I'm seeing with these two functions is they undo what the other one does. F, for example, f of 5 is equal to 3 times 5 plus 2, which is 15 plus 2, which is 17. So the function f takes an input of 5, gives an output of 17. The inverse function undoes that. It takes the output and gives back the input that you started with. So for example, f inverse of 17, I'm going to take this function, I'm going to plug in 17, I mean 17 minus 2 divided by 3, which is 15 divided by 3, which is 5. It undid what the original function did. The original function took 5 as an input, gave 17 as an output. The inverse took that output of 17, put it inside its input, and gave back the 5 we started with. So when I talk about things undoing what the other one does, this is what I mean, that they undo what the other one did by reversing the process. Derivatives and antiderivatives have a similar effect on functions. Let me show you what I mean. Yeah. So let's say our function f of x is, let's say not something too terrible here, 3x squared plus 4. Yeah, sure. The derivative of that is going to be 6x plus 0. Sorry, I'm way off here. So here's our function, here's a derivative. And then we can say, and here's where the notation part kind of gets messy. So let's go over here. If our function is g of x equal to 6x, the antiderivative there's a lot of ways to write this. We can write it as capital G of x as a kind of an accepted notation for an antiderivative, or you can write it as this symbol, the integral symbol of g of x dx. We're literally going to undo the derivative. So when I say antiderivative, I'm really just thinking of, I need to find the function whose derivative is equal to 6x. Well, 3x squared is going to fit the bill. But now we have a problem. Because I could add 4, but I could really add anything. I could add 7, or 9, or 13.2, or pi, or any constant that you like. So what we usually do when we're finding general antiderivatives is we say we're going to add on a plus c. And as far as we're concerned, this is close enough. Yes, I recognize that these aren't exactly the same. 3x squared plus c and 3x squared plus 4 are not precisely the same function, but they're close enough. They differ by, at most, a constant. These two things have undone each other. This process here where we differentiated went from 3x squared plus 4 to 6x. This process here where we anti-differentiated went from 6x to 3x squared plus close enough. But it is always going to be close enough, unfortunately. It's not always going to be exactly the same. But this is what I really want you to take to heart, is that this process of differentiating and anti-differentiating undo each other. You could do a derivative and an antiderivative and end up almost back where you started. You could do it the reverse way and end up exactly back where you started. Let's actually see that. Let's look at 2 more examples. And then I guess, well, sorry, we'll look at 2 more examples in a second. Let's talk for just one moment about some notation stuff. So derivatives and antiderivatives. Also, you might notice that maybe, antiderivative, you might notice my spelling is not always excellent. Antiderivatives. Sure, it's a long word. Things might not always seem maybe the most organized that they could be, and that is a fact of me. So apologies, I'll try to be organized, but bear with me. So if I say that my function is f of x, the antiderivative can be written in a couple ways. I would generally say this is the way that eventually we'll be writing it, but often we haven't introduced this yet. And so that is a elongated S. It's called the integral symbol, and that is the integral of f of x dx. And I feel like I need to grab some. You know what? I forgot about something I was doing last quarter that made it easier for people to read what I was writing. I think I might need to order some new pens. Yeah, there we go. I think these pens are almost out of ink though. Okay. Let me try that again. Pen's a little bit thicker. Okay, that makes it a little bit easier to see what I'm writing. Yeah, is that better? I think it's better. So this is kind of what we're going to use eventually, but for now, you might write it as capital F of x. Usually the capital letter is generally accepted as the antiderivative. Or you might write that the antiderivative of f prime of x is f of x. Seems reasonable. If you're finding the antiderivative of the derivative of f, you're going to get back to the function you started with. I think this kind of sums up the nature of derivatives and antiderivatives as concisely as it can be. That's really all there is to it. I know it feels like there's kind of a lot to it. And yes, there are a lot of methods for how we anti-differentiate various types of functions. But when it comes right down to it, you're just looking for the function that you can take the derivative of to end up where you started. So, for some examples here. Sure, we can look at these examples. Let's say the function that we want to anti-differentiate, we'll call it f prime of x, is 2x to the third plus 6x squared plus 4x plus 5. I want to find the antiderivative of this. So I'm going to use what I typically call the anti-power rule, which I'll write down in a second, but we're just going to use it right now. So the rule here is you're going to undo what the derivative does. The power rule for the derivative, we multiply by the power and then we subtract one from the power. For the antiderivative, we're going to undo that in the opposite order. So instead of multiplying by the power and then subtracting one from the power, we're going to first add one back to the power and then divide by the power. We're really just undoing what we did in the opposite order. So I'm going to add 1 to the power and divide by that new power. I'm going to do the same thing over here. Oh, and I should write f of x equals. I'm going to get 6x to the 2 plus 1 divided by 2 plus 1 plus 4x to the 1 plus 1 divided by 1 plus 1 plus the so this is kind of what the handout actually was getting at, was that the antiderivative of a constant is that constant times x. And then, yes, we're going to tack on another general constant over there. Now, I would expect most of us can probably get past writing the 3 plus 1, or the 2 plus 1, 1 plus 1, and just say, yeah, we know what those things are. This is going to be 2x to the 4th divided by 4, plus 6x cubed divided by 3, plus 4x squared divided by 2, plus 5x plus c. And then I would simplify this as 1/2 x to the 4th plus 2x cubed plus 2x squared plus 5x plus c. And the point of this really is that if we take the derivative of this, we should exactly get that. If we take the antiderivative of this, we should exactly get that. The antiderivative is just the thing that we would be able to take the derivative of to get us back to where we started. You don't usually have to do that, but it's important that it is true that if we did that, we would get back to where we started. Let's double check. I know it's written down here, but let's check anyway. The derivative here would be 1/2 times 4x cubed plus 2 times 3x squared plus 2 times 2x plus 5 times 1 plus c plus 0. Holy smokes, plus 0. What's the derivative of a constant? 0. And then if we simplify this, we exactly get what we have up here. 2x cubed plus 6x squared plus 4x plus 5, which is exactly that. Plus, we're not required to show that work typically, but it's important that if we were to do that, that we would get back the function that we started with. Let me look at the Zoom here. Sorry, I'm missing the questions over here. I apologize. So for an antiderivative problem, we would get the derivative of something and take the antiderivative of it. Well, so again, this is where the notation, so notationally, you can ask this a couple different ways. Often at this point, we'll say, here's the derivative of the function, find the original function, which is the same thing as just asking for the antiderivative of this function. I could also write it out in words. Let's look at another example. We could say something like, find the antiderivative. What is that noise? Weird. I wonder why that started happening. Find the antiderivative of g of x equal to x squared plus 3 times x to the 4th plus 2x. So in this case, it kind of depends on what you want to write. If it were me, I would probably write it as, well, I'm going to simplify first, but I would write it as g of x, capital G of x, equal to. So in the previous problem, since the original thing we had started with, we had called f prime, its antiderivative was just regular f. But here, since the original function we're starting with, we're calling g, its antiderivative is going to be capital G. But really, the truth is, eventually, we're going to start just using the integral notation to mean the antiderivative. But we haven't really defined it yet, so it kind of feels silly to use it. So hopefully that clarifies the question on Zoom there. So before I can do this, I have to multiply this out. So let's FOIL this out and see what we get. Little g of x is equal to x squared times x to the 4th plus 3 times x to the 4th plus x squared times 2x plus 3 times 2x. And now for each of these separate things, I'm going to use the anti-power rule. I'm going to get x to the 7th divided by 7 plus 3 times x to the 5th divided by 5 plus 2 times x to the 4th divided by 4 plus 6 times, this is x to the first here, so I'm going to get x to the 2nd divided by 2 plus a constant. And then I'm of the mind that we should simplify these things if we can, because they're not that terrible. I would write this as, and this is kind of a matter of preference. You can write this as x to the 7th over 7, or you can write it as 1/7 times x to the 7th. Either way is correct. I can write this as 3/5 times x to the 5th. Here, I do need to simplify, though. This 2x to the 4th over 4 should either be x to the 4th over 2 or 1/2 times x to the 4th. Same deal here. 6x squared divided by 2. 6 divided by 2 is 3. So we should write this as 3x squared plus c. That is a c, not a 6. Right. For f of x, well, no, not really. So someone is asking, for f of x, we could have used the integral notation as well. And I mean, yeah, sure. We could have, I suppose, in this previous problem said that the integral of f prime of x dx is going to be what our f of x was, which was exactly that. That would have been fine to use. I would try not to get too caught up with the notation right now. It's going to be kind of not that big a deal. Yeah. Questions so far? Oh, I know what I can say. So here is the anti-power. Anti-power rule. I don't think this is actually, by the way, this is probably not the official name for this rule. It's just like, I actually don't know if there is an official name for this rule. It's what I've always called it. The anti-power rule says that the antiderivative of f of x equal to x to some power is, let's go ahead and use the capital letter notation. Capital F of x is x to that power plus 1 divided by the new power, which is that power plus 1. And then we slap on a constant. And this always works, except for one possible power, which is problematic. What value of p looks like it might be an issue if we end up dividing by p plus 1? Yeah, we can't have p be -1 because if it was, we'd be dividing by 0. So this anti-power rule works as long as p is not equal to -1. So this works for any positive power, any negative power, any fractional power. So for example, we could be given something like dy dx, the derivative of y, equal to x squared plus 3x plus the square root of x plus 5 divided by x, and be asked to find the antiderivative. The antiderivative of the derivative is just the function. So we want to find y. Most of these problems at this point, before we can find y, we might have to do some simplifying, right? I don't just have x to a power. So I can't just throw the power rule at it or the anti-power rule at it. Oh, and I should point out, yeah. So if you need to leave early ever, that's totally fine. If you need to come late, that's totally fine. Also, as I've said in previous classes, this is the least important class you're taking as far as like doing the stuff, right? This class is the bottom. All your other classes that count for actual grades and real units, those are a priority. So if you have like a class after this you need to go to, or a test after this that you need to feel mentally prepared for, feel free to leave early or not come at all and make up attendance later. Whatever you need to do is really fine with me. If you need to use the restroom, whatever, like you don't have to ask me for anything. Leave, come and go as you please. Really, really fine. So anyway, for this problem here, I need to simplify this expression before I can find its antiderivative. So I'm going to divide each thing by x, like it's written here. So dy dx is really x squared divided by x plus 3x. Well, we'll get there, sure. 3x divided by x plus the square root of x, I'm going to write as x to the 1/2 divided by x plus 5 divided by x. And I'm going to simplify these things. And I'm going to have a problem, but that's all right. I'll deal with it. So x squared divided by x is x. 3x divided by x is 3. X to the 1/2 divided by x to the 1. We subtract those powers and we get x to the -1/2. And here I've got 5 over x, which I could write as 5 times x to the -1. But specifically when the power is -1, we know we can't use the anti-power rule. And I prefer not to write it like that because it's harder for me to see what I need to do. So I would prefer to write this as 5 times 1 over x. I feel like that's the easiest way to know what I'm supposed to do next. So now we're going to find the antiderivative. For these first 3 terms, we're just going to use the anti-power rule. The antiderivative of x to the first is x to the second divided by 2. The antiderivative of 3 is, constants always just get multiplied by x because the derivative is just 3. And here for this x to the -1/2, we're going to x to the Negative 1/2 plus 1 is positive 1/2. And then we divide by the new power. And then we have this thing over here. So as with derivatives, constant multiples like to hang out for antiderivatives as well. So if you have a function multiplied by 5, by 7, or by any constant, that constant multiple just hangs around. So that 5 is going to hang out. And then we have to ask ourselves, what's the antiderivative of 1 over x? Or as I like to phrase it, what function can you take the derivative of and get 1 over x? The natural log. Now, here's an unfortunate actuality. It's not just the natural log of x. It's actually the natural log of the absolute value of x, which is annoying, but true. We can talk about why in a second. And then, of course, we need a plus c at the end here. So simplifying this a little bit, I really don't want to leave these fractions and fractions here. So this part specifically, I should rewrite as 2 over 1 times x to the 1/2, or just 2 times x to the 1/2. So I would rewrite my answer as x squared over 2 plus 3x plus 2x to the 1/2, or 2 times the square root of x, whatever your preference is there. Either way is totally fine. And then plus 5 natural log of the absolute value of x plus c. So there's the antiderivative of this expression up here. Even though we gave it a regular function name, it's still the antiderivative of that thing. Oops, of that thing. Sorry. All right. I'll give you all one. Question, is Dedel going to want us to simplify like this? Probably. I don't, but again, I'm not really the person you should ask. He actually knows what he wants you to do. So if you have a question about how your teacher wants you to do something, I can give you my best guess, but really you should ask them how much simplifying they expect. Yeah. But yeah, I mean, certainly most people would expect you to do that simplification, to rewrite this as 2 times the square root of x, or you could also write this as 2 times x to the 1/2. But division by a fraction, we usually always want to multiply by the reciprocal to make that nicer. So I think you all try one on your own. Let's say that we have the derivative of f is, sure, I'm gonna make you multiply some stuff out. Yeah, why not? Let's say we have x cubed plus 4x times x squared plus, ooh, yeah, let's make it fun, the square root of x. It's a little gnarly. So I want you to multiply this out and then find the antiderivative. And I would definitely recommend replacing x square root of x with x to the 1/2. Give you a minute or two to work on that. We end at 10:20, right? There's the multiplying out if you want to check what your work looks like, and then you still need to anti-differentiate that. What? That's exiting. Yeah, it's that's next to the third, not next to it. And yes, and just as a reiteration, if you ever need me to clarify something I've written or say it again, because it's hard to read, which I fully admit my handwriting is mediocre at best. Please do ask. I'm always happy to clarify and I will not be offended. So let's actually talk about how this multiplying out works here. So when you have x cubed times x squared, we're using the additive law of exponents and we're just adding the exponents. So 3 plus 2 is 5. Same deal here. X to the third times x to the 1/2, we add the powers and we get x to the 3 plus 1/2, which we're going to simplify in the next step. 4x times x squared, you have x to the first times x squared, so 1 plus 2 is 3. And then finally 4x to the first times x to the 1/2, we add the powers and get 1 plus 1/2. In the next step, we simplify those. X to the fifth is still x to the fifth. 3 plus 1/2 is really 6/2 plus 1/2, which is 7/2. And similarly here, 1 plus 1/2 is really 2/2 plus 1/2, which is 3/2. That's part of there. And then we're ready to anti-differentiate. So then for each of these x to a powers, we're just going to add 1 to the power and divide by the new power. So for the antiderivative of x to the fifth, we're going to get x to the sixth divided by 6. For x to the 7/2, okay, we're going to have to, so there are going to be a lot of adding of fractions, specifically adding 1 to a fraction. So if I'm adding 1 to 7/2, I'm really just adding 2/2 to 7/2. And 2/2 plus 7/2, well, 2 plus 7 is 9. So I'm going to get x to the 9/2 divided by 9/2 plus 4x to the fourth divided by 4 plus 4x to the 3/2 plus 2/2 is 5/2. And eventually you're going to do this enough that you're going to get tired of dividing by a fraction. You say, okay, instead of dividing by 5/2, I know I'm going to end up multiplying by 2/5, which looks terrible the way I've written it. Sorry. But we're going to simplify it anyway. So then we're going to rewrite this as x to the 6th over 6. Dividing by 9/2 is the same as multiplying by 2/9 times x to the 9/2. 4x to the fourth divided by 4 is just x to the fourth. And finally, 4 times 2/5 is 8/5 times x to the 5/2. Let's see. And yes, if you're finding a general antiderivative and you're not solving like an initial value problem, then you have to add a plus c at the end. So technically, it's kind of weird, but technically this function has an infinite number of different antiderivatives. It could be all this plus 1, or all this plus 2, or all this plus, take your pick of constants. But we kind of just group them all together and say, okay, this is the family of antiderivatives of this particular function. And they all just differ by a constant. But that actually does bring up an interesting question. What about these initial value problems? So sometimes you're going to have a question where, in addition to being asked to find the antiderivative, you're also then given some initial condition and asked to solve for the value of the constant c. So for example, someone might say something like, given that f prime of x is equal to, sure, let's make it fun, say x to the third plus the cube root of x plus 4x. Yeah, sure, plus 5. I like it, plus 5. Oh, sorry, yep, see, there we go. So given that, and that f of 1 is equal to 9. 9, sure, 9's fine. Find the particular solution. F of x. Meaning there is one and only one function whose derivative is all this, and when you plug in 1, the function is equal to 9. So first we're going to do the usual thing. We're going to find the antiderivative. So I want you all to find f of x, the general f of x. So I'll remind everybody that the cube root of x here is just x to the 1/3 power.
They give us like f of 1 equals 9 and like f of 5.
I'm imagining that problem you're starting off with a second derivative, not a first derivative. Yeah, we'll talk about that in a second. Yeah.
A derivative, and it just gave us the 2 conditions for f. It was like,
Whether you mean the second.
but it only said that f0 equals that and that f pi equals that. It didn't give you what, like, the, it didn't give you.
Right.
That,
You're right.
there's two different values.
You're right, it doesn't. So we'll talk about it in a second. It is solvable, but it's a little bit more work. So if we have that the derivative is x to the 3rd plus x to the 1/3 plus 4x plus 5, we're going to antidifferentiate. I know I'm not giving you a lot of time because we have 15 minutes left. So it's always, I always feel like I'm rushing people. I try not to, but there's so many things to say. So let's do the antiderivative here. We're going to get x to the 4th divided by 4 plus x to the 1/3 plus 1 is 1/3 plus 3/3. That's going to be x to the 4/3. And instead of dividing by 4/3, I'm going to multiply by 3/4 plus 4x squared divided by 2 plus 5x plus c. And yes, we could simplify this a little bit. I don't really want to, but I will. Simplifying is not really anyone's favorite. This is x to the 4th plus 3/4 x to the 4/3 plus 2x squared plus 5x plus c. And then we plug in the stuff. So we're going to say, okay, x is 1 and f of x is 9. So I'm going to say that 9 is equal to 1 to the 4th over 4. Fun fact, 1 to any power is always 1. I don't want to write 1 to the 4th. You don't want to write 1 to the 4th. I know that 1 to the 4th is 1. I know that 1 to the 4/3 is 1. And that anything times 1 is still itself. 1 squared is 1. So 2 times 1 squared is just 2. And 5 times 1 is 5. So then I'm going to add all this together. And fortunately, the fractions work out nicely here. 1/4 plus 3/4 is just 1. And 1 plus 2 plus 5 is 8. So 9 is equal to 8 plus c. So c is equal to 9 minus 8, which is 1. We're not quite done with this problem. There's one more thing we have to do. We have to write the actual solution with this value of c plugged in. So our actual solution, which I feel like I didn't leave myself enough room for here, but I'll try to write it somewhere. Our actual solution is that f of x is equal to all of this, x to the 4th over 4 plus 3/4 x to the 4/3 plus 2x squared plus 5x plus 1. That's our actual answer to this question. The answer is the function. People have some good questions about this other situation where you have a little bit more to figure out. So let's look at another example. I'll try to make something up where the answer is don't come out too terribly, but no guarantees here. Let's say we're given the following. So we're given that f double prime of x, the second derivative of f, is equal to, sure, I'm trying to make things not incredibly awful here, 12x squared plus 8x plus 9. 9's a terrible choice. Let's make that 8. And we were told that f of 0 is equal to 7 and f of 1 is equal to -2. With this information, we can find the function f. It's going to be a little bit terrible, but not that bad. Sometimes I will point out, sometimes these problems give you a value for f prime. Sometimes they give you just values for f. As long as you have two pieces of information, you can always figure out what the constants are to solve a problem like this. It doesn't matter if you're given f or f prime. So let's start by antidifferentiating. So the antiderivative of f double prime of x is f prime of x. So I'm going to antidifferentiate this. So the antiderivative, which is f prime, is going to be 12 times x cubed over 3 plus 8 times x squared over 2 plus 8x plus, we know we're going to end up getting two constants here. I usually like to use C and D, but I feel people generally prefer C1 and C2. So let's call this one C1. And if I knew what f prime of something was, I would plug that in right now and then solve for C1. But I don't have an f prime of anything, so I move on. Actually, before I move on, I simplify. I should really write this as 4x cubed plus 4x squared plus 8x plus C1. And now we're going to be sad that I made a poor choice with my constants, but such is life. We're going to antidifferentiate again. We're going to get f of x equal to x to the 4th plus 4x cubed over 3. That's what I'm kind of sad about, but oh well. Plus 8x squared over 2, which is going to be 4x squared. Plus the antiderivative of a constant is that constant times x plus another constant. That's what usually happens, right? If you can't solve with the constants along the way, right? If you can, whenever you antidifferentiate a constant, you just get that constant times x. Now we're going to plug in the pieces, the initial conditions here, and try to figure out what C1 and C2 are. And I would say that if you have one of them where the value that you're plugging in is 0, use that one first. So using the f of 0 equals 7, so x equals 0 and f of 0 equals 7, then I'm going to say that 7 is equal to 0 plus 0 plus 0 plus 0 plus C2. Or cutting out all the writing, C2 is equal to 7. Great, that's not terrible. And then to find the other constant, C1, I'm going to plug in the other value here. So I'm going to say that f of 1 is -2. So x equals 1, and the function is equal to -2. So -2 is what the function is equal to, and it's equal to 1 to the 4th plus 4 times 1 cubed over 3 is unfortunately 4/3. Plus 4 times 1 squared is 4. Plus C1, which is the thing we're trying to solve for, times 1. I don't think I'm going to write times 1 there because I know that C1 times 1 is just C1. Plus C2, which is 7. And now we can solve for C1. So it's not my favorite, but I have, let's see, on the right-hand side here, 7 plus 4 plus 1 is 12. So I have -2 equal to 12 plus 4/3 plus C1. I'm running out of room. We can use more paper. So then writing that down again. You know what I could do to make my life easier, which I just thought of now? I really don't want to add 4/3 to 12. What could I do to this equation to not have to deal with fractions? What can I multiply both sides by? 3. It's totally valid for an equation. So multiply both sides by 3, -6 equals 36 plus 4 plus 3 times C1. And now my life just got a lot better, I think. So then -6 equals 40 plus 3 times C1. Subtract 40, -46 equals 3 times C1. And C1 is unfortunately something not very lovely, but it's -46 divided by 3. Not the best thing ever, but sometimes you get not nice numbers. And then finally, we actually go back and write our function. So our function f of x, I think I can calculate this here. F of x, looking back up here for a second, it's going to be all this, but we're going to plug in -46 over 3 for C1 and +7 for C2. So we're going to get x to the 4th plus 4/3 x cubed plus 4x squared minus 46 over 3 times x plus 7. So that's how you deal with these second derivative initial value problems, where you have to find two c's. Typically, you do all the integrating to get your function, and then after you found the general, the general version of f of x here, then you go start plugging in your initial conditions to figure out what the C1 and the C2 are. 10:14, okay. We end at 10:20. Yes, I said that before, but I'm saying it again. So, yeah, let's do that. I mentioned before that the derivative of the natural log of x, or sorry, that the antiderivative of 1 over x is the natural log of the absolute value of x. There is a reason for that, and it has to do with the domain of the function. So let's talk about it really quickly, and then we'll call it a day. And then I guess on Thursday, we'll talk about the Riemann sum stuff, because that definitely is showing up in both classes. So yeah, let's go there. So question, why is the antiderivative of 1 over x equal to the natural log of the absolute value of x plus c? Good question. Why is that the case? Well, let's go the other direction for a second. We know that the derivative of the natural log of just x is 1 over x. Graphically, here's what's happening. So here's the natural log function. What's this x-intercept here? Yes, it's 1, 0. Also, if no one's ever showed you this before, my hand's not the best because, you know, I'm old. But if you look at your right hand, oh God, can you see that even? I should really ask one of you to come up here, but most of you have like a line here on your right hand, like your right hand, that looks like the natural log function. And similarly, you have a line here that kind of looks like the e to the x function. I think it's kind of great. So remember the natural log function, it has a vertical asymptote and it has an intercept of 1, 0, and it keeps getting bigger and bigger and bigger. It just slows down, but it does increase forever. Yeah. Not at all. So when you talk about the derivative of this, the graph of 1 over x would actually be too much, because really, when we talk about the derivative being 1 over x, we really mean 1 over x when x is greater than 0. We only get this half of the y equal to 1 over x function. So here's f of x equal to the natural log of x, and here's f prime of x equal to 1 over x, as long as x is greater than 0. And that's because the original function here, the natural log of x, its domain is when x is positive. So here, the domain is naturally x is greater than 0. Or if you want to use the interval notation, that. But for a function to be differentiable, it has to exist. It has to be defined, and it has to be continuous as well. So for this derivative to exist, it can only exist where this original function was defined in the first place. So that's why when we talk about the derivative being 1 over x, we're limiting ourselves to 1 over x when x is greater than 0. Okay, but now, if our starting place is f of x equal to 1 over x, well, the natural domain for that function is everything except for 0. So this function, f of x equal to 1 over x, looks like this. There's your usual 1 over x function. And the antiderivative of this really should be defined on both sides of the y-axis, when x is positive and when x is negative. So we define the antiderivative, which I'm going to write as capital F of x, to be the natural log of the absolute value of x. I don't want to write the plus c really, although there would be a plus c. Which looks like the regular natural log function on the right-hand side. And the reflection of the natural log function across the, oh, it just froze there. I don't know what I did, but something happened. It froze. That's wonderful. Just, oh, great. Okay, there we go. The other side looks like this. Let's see how well I can draw this reflection here. Which makes some sense if you look at the graph, right? So over here, this, and wow, that's really not my best reflection ever, sorry. So I'll point out on the left-hand side, the function here is increasing or decreasing. What was that? Decreasing, for sure. Getting smaller from left to right. If the function is decreasing, the derivative should be over here. The derivative is definitely negative, right? This function is negative. It's always below the x-axis. On the right-hand side, the function, this original function is increasing. And the derivative over here is positive. I know it's getting smaller, but it's above the x-axis, so it's positive. So here, the derivative is negative. Here on the right-hand side, the derivative is positive. Here on the left-hand side, the function is decreasing. Here on the right-hand side, the function is increasing. So because of domain issues, the antiderivative of 1 over x isn't just the natural log of x, it's the natural log of the absolute value of x. And that absolute value is necessary. It's not just like something we can forget about. So yeah, all right, I should stop talking. It's 10:21. I'll be over in C class at 10:45, and I'll see you all on Thursday.